Hello, everyone. So I'm sorry I couldn't join today, but I've recorded this presentation for you. This is part of the work I've conducted at UCLA as a postdoc. I worked on the dynamics of internal tides, internal waves, and this presentation is more specifically about their interaction with the atmosphere and how this can create a dissipation mechanism. The work has been done in close collaboration with Roy Barkan from the University of Tel Aviv, with Lionel Renaud from the IRD in France, and with James McWilliams from UCLA. So I will start this presentation with some element of context and some motivations, and then I will present the regional simulations that really are the key of this study. We really rely on these regional numerical simulations. And then I will present what we call the internal wave killing mechanism, with the mean energy sink, the mechanisms underlying, and the energy sink variability before concluding. So first of all, some very basic knowledge about internal waves. Internal waves are inertial gravity waves that propagate at the interface between two layers of different density. And because the ocean is continuously stratified throughout the water column, they propagate inside the ocean. There are several generation processes for internal waves, and we're going to focus on two of them particularly, which is on one side the winds and the storms, which can create inertial oscillation in the mixed layer that pumps or makes the basis of the mixed layer oscillates and can radiate away internal waves at the frequency close to the inertial period. So that's why they're called the near inertial internal waves. Another generation mechanism is when tidal barotropic tidal flow flows along or above a seamount or ridges, and that can create that can also radiate away internal waves at the frequency of the tidal frequency, and we call them tidal internal waves. There are also like some other generation mechanisms, such as deep currents flowing over rough topography that can create lee waves. But because those waves are mostly trapped at the bottom, we're not going to consider them in this study because we will be interested in the surface expression of these internal waves. So just to give you an idea how important internal waves are in the ocean energetics, we can look at the spectrum. So here, the energy as a function of the frequency. So here is data taken in the Northeast Pacific Ocean at 150-meter depths. And what you can see, I hope you can see my pointer, what you can see that there are two peaks of energy at the inertial frequency F and the M2 tidal frequency M2 here. And so these two frequencies, these internal tidal and inertial internal waves, are really major energetic feature at depths. So why do we study internal waves? So first of all, for the global ocean energy budget, as I just said, internal waves constitute a large reservoir of energy in the ocean, and their dissipation actually generates small-scale turbulence, and it's the principal source of dipycnal mixing, which is key to maintain the global overturning circulation and drives vertical fluxes of heat, CO2, and nutrients, for example. As an illustration, here you have the famous chart by Monk and Wunsch in 1998 that shows that the forcing of the moon, the sun, and the winds over the ocean generates mostly distributed or localized turbulence in the water column that is key to maintain the abyssal stratification. And this goes through internal waves generation processes. The second reason why we're interested in internal waves is to better understand and interpret the new generation of satellite altimeters, such as the SWAT satellite, the wide swath altimeters that can measure ocean topography at very small scales. And at these very small scales, the ageostrophic component of the sea surface height, which is mostly driven not only by internal waves, really matters. And so understanding or better understanding their generation, propagation, and dissipation is really key in the interpretation of this data. Although they're called internal waves, those waves have a surface expression. They have a surface signature, both in sea surface height and also in velocity. Here you have a global map showing the surface elevation associated with the M2 internal wave. It's coming from a model, but you can see that those waves are present in all ocean with some generation hotspots, such as the French Polynesia or the Hawaiian Ridge here. And they do have a surface expression. And we know that surface processes can interact with the atmosphere through the atmospheric boundary layer. And so here we're going to focus on one of these interaction process, which is called the current feedback mechanism. So the current feedback is just a way of taking into account the local currents into the wind stress expression and its retraction on the currents in the ocean. The current feedback mechanism has been shown to be a major or quite important mechanism for the dynamics of the eddies in numerical models. It allows a better or more accurate representation of the oceanic eddies in numerical models. There have been several papers on the topic, driven mostly by Lionel Renaud, but not only. And in a recent study by Ray et al. In 2021, there has been a global evaluation of the energy sink associated with the eddy killing mechanism, which is the way of, like, because the current feedback is actually damping, is acting as an energy sink for the oceanic eddies. We can compute the associated energy sink. It's been estimated of being 50 gigawatts at a global scale, which is not, I mean, it's a large value compared to the inputs in the mesoscale eddy field. And so now one question arises is, can the current feedback affect oceanic internal waves as it affects oceanic eddies? And what would be the implication for the internal wave energy budgets if that were the case? And so to answer these questions, we've conducted a set of numerical experiments. So we've chosen the region of the California current system. Here, the region we're modeling is here in the black box. And so why this region? First of all, because it's one of the regions where there is a internal tide generation hotspot. Internal tides are generated at the Mendocino Ridge that you can see here on this map. And then this map represents the amplitude of the M2 internal tides compiled from 25 years of conventional satellite altimeters. And you can see beams of internal tides propagating away from the Mendocino Ridge northward and southward here. So yeah, this region is really a hotspot for internal waves generation. It's also a region where we will have some in situ data to compare with and to validate the models, because it's one of the regions where there's been, which is part of the SWOT calibration and validation experimental sites. Just a few words on the setup of the numerical simulation. The simulation has been conducted in a Croco model. So here you can see a snapshot of the surface vorticity. It's been conducted at a 2-kilometer grid spacing. So it's mesoscale resolving, sub-mesoscale permitting. The external boundary are forced for the low frequency part with a coarser simulation of the same Croco model, and for the high frequency part with a HICOM model, which is well known to represent accurately internal waves and internal tides in the ocean. So we not only have the local generation, or the internal tides are locally generated at the Mendocino Ridge, but also the one coming remotely from, for example, the Hawaiian Ridge and propagating into the domain. For the atmospheric forcing, we have a WRF simulation, a high-frequency WRF simulation, and the current feedback is implemented as a parametrization in this simulation. It's based on the stress correction approach, which is implemented and described in Renaud et al. In 2020. And the idea of this stress correction approach is just to add a correcting factor to the wind stress in the simulation to account for the local currents. So we've run this simulation for a year, and based on the results, we were able to compute the co-spectrum of wind and surface currents, which is shown here as a function of the horizontal wave number and the frequency on the y-axis. And the way to interpret this figure, so it's 1 year average here, is that when it's positive, it means that there is an energy transfer from the wind into the ocean. And when it's negative, there is an energy transfer from the ocean to the winds. And so what we can see here is that there is mostly an energy input at large scales, as you can see here on the left-hand side of this figure. In the mesoscale and submesoscale range, there is an energy loss that can be related to the eddy killing mechanism we've been talking earlier, and well documented in different papers, for example, Renaud et al. In 2016. But which was less known is that we also have energy loss at higher frequencies, especially in the near inertial frequency range, and at the M2 tidal frequency, 12 hours here, and along the dispersion relation of the different internal waves. And so we asked ourselves if we could call this an internal wave killing mechanism, if this could be related to the eddy killing mechanism, or be like the same thing, but just for internal waves. So the word killing is not quite correct. Damping would be more accurate, but just because it was already mentioned in the literature as eddy killing, I just picked up the same word. So the question that arose from this was how much this energy loss represents compared to the generation or to the power of those internal waves. Oh yeah, just before this, and just to convince you that this energy loss is really due to the current feedback mechanism, I've run a set of simulation with the current feedback and without the current feedback parametrization. And what you can see that when we don't have the current feedback parametrization, we also don't have this energy loss, neither in the mesoscale, submesoscale range, or in the high frequency range. So it's really related with its current feedback parametrization. So the question, like I was saying, is how important is this energy loss in the total energy budget of the internal waves? And to quantify this, I've computed the power input into the internal waves. So here it's focused on the M2 internal tides, which is a dominant feature in the region. I've computed the W prime B prime term, which corresponds to the barotropic to baroclinic conversion. So the amount of energy that goes from the barotropic tides into the baroclinic tides. And average over the whole domain, we have, or sum of over the whole domain, we have a 1.6 gigawatts power input into M2 internal tides, mostly located along the Mendocino Ridge and along the continental shelf break. Now, if we compute the same thing, the wind power over the ocean at those frequencies, exactly the same scales. So the U prime tau prime term, where tau here is a wind stress, we get a total of 0.13 gigawatts. And if we make the ratio of those two numbers, there is approximately a 10% difference. So we can conclude that the energy sink due to the wind work is about 10% of the barotropic to baroclinic conversion at those frequencies. Just to illustrate the fact that this energy or this energy loss is really an energy loss for the internal waves and not for, or the tidal internal waves and not the barotropic tides, I've done this computation by separating the barotropic currents and the baroclinic currents. And all of this 0.13 gigawatts is really coming from the baroclinic currents. So it's really like the internal waves that are that have or that lose this energy. So the mechanism behind it can be explained by looking at a chart or a graph of how the wind work relates to the current, the phasing of the wind work relates to the currents. the wind stress, sorry, relates to the currents. And so the wind stress with the current feedback is defined as follow, and it includes the difference between the winds vector and the ocean current vector. The wind power scales as the wind stress times the local current. And so if we assume that we have an internal wave with a constant wind blowing over it, and that this internal wave has a given period with the current reversing from southward during the first half of the period to northward during the second half of the period, and the wind is blowing constantly southward, then because of those definitions, the wind stress during the first half of the period will be much smaller. And as a consequence, the wind work, which is the wind stress times the currents, will be small and positive because the currents and the wind stress are in the same direction. To the contrary, if we have during the second half period, the wind stress will be much larger because the winds and the currents are opposite direction. And the wind work will be large and negative. So on average, over a period, we will have a negative wind work. But of course, this is idealized because internal waves are not, the currents associated with internal waves are not like reversing strictly like that, and they are polarized along a given direction, which cannot be aligned with the wind, but have a certain angle with the wind. And so there will be an angle effect to take into account. And actually, if we compute this wind work, or at least this part of the term of the wind work, as a function of the angle between UW, which is the wind vector, and U, which is the ocean vector, and we represent this as a function of this angle, so this is what is shown on this polar chart here, we can see that we have a much larger, so this is negative here, we have a much larger coefficient, a much larger negative wind work when the winds and the currents are aligned, so for 0 angle and 180 degree, and smaller wind work when the winds and the currents are perpendicular. And so the energy sink is twice more important when the winds and the currents are aligned. So the question that we could ask is, can the wind direction variability, because we know the wind changes direction seasonally, for example, modulates this internal wave killing mechanism and the associated energy sink? So to investigate this, we've computed the same wind work, but as a function of time instead of taking a yearly average. And here is what I'm showing. So these figures represents the U prime tau prime as a function of time for the different seasons. And here the numbers above this chart represents the average for each season. And what you can see is that on average, the wind work is smaller in winter and larger in summer. And on the bottom panel is the average wind direction over the domain as a time series, and here as a wind roses. So it's more statistical here on this bottom panel. And what we can see is that while in winter, the wind is spread over all the direction and do not have a particular direction, in summer, the wind is more aligned or blowing more constantly in the same direction, which is the southwest direction. On average, the currents associated with the M2 internal tides are aligned in the south-southwest direction. They're indicated by this blue arrow that we can see here. And so as a result of this, the winds and the currents associated with the M2 internal tides are more often aligned or more frequently aligned in summer compared to winter, and that could explain why the energy sink is stronger in summer than in winter. just because we've seen that there is this angle effect, we've also investigated the energy sink as a function of the modes, because we know that the different modes are polarized differently. And so we've computed the energy sink or the internal wave energy damping due to the current feedback for mode 1, mode 2, and mode 3. And it actually increases with the different modes. It's 2.6% of energy loss for the mode 1, and 9.3 for the mode 2, and 11.8 for the mode 3. And again, we've looked at this time, this is the yearly wind rows. So this is the yearly wind statistics. So the angle, the statistical, the angle of the wind direction is represented at the angle on this chart, and the density of probability is the radial radius of this bar chart. And what you can see here is that on average, the wind blows more constantly in the south-southwest direction, while mode 1, so here it's the same for the currents, the mode 1 is polarized in the east-west direction. So the alignment of the wind and the current associated with mode 1 is not optimal for this energy sink. On the contrary, if we look at the current roses for mode 2 and mode 3, they're more, so mode 2 is more north-south, and mode 3 is really like northeast, southwest. So exactly the same direction as the wind, actually. And so that could explain why mode 2 and mode 3 are more damped or more affected by this energy sink than mode 1. And why is mode 1 more in the east-west direction, polarized in the east-west direction, and mode 2 and mode 3 more polarized in the north-south direction, can be explained by the origin of these internal waves. So if we decompose the surface kinetic energy between the different modes, so mode 1, mode 2, and mode 3, we can see that mode 1, so we can also look at the flux, which is not shown here, but mode 1 is mostly remotely generated and propagating into the domain from the outside of the domain. It's actually more generated not locally, but at the Hawaiian Ridge, and then it's propagating into the domain from the west to the east. And that explains why the currents are polarized in the east-west direction on average. Mode 2, on the contrary, and mode 3 are locally generated at the Mendocino Ridge, and they propagate in the north and south directions. And that also explains why they're they're polarized, their currents, associated currents, are polarized in the north-south direction. This was already documented, the fact that mode 1 is in this region is mostly remotely generated, and that the Mendocino Ridge generates higher mode was also documented in a paper by Althaus in 2003. So as a conclusion, we can say that this study has shown that internal waves, that current feedback has an effect on internal waves. It can generate a negative windwork, which induces a net energy sink for the internal waves. For the tidal internal waves, this energy sink is estimated to be approximately 10% of the production of the barotropic to baroclinic conversion. There is a seasonal variability in the magnitude of this energy sink. It's stronger in summer and weaker in winter. And this can be explained by the alignment of the winds with the surface currents associated with those internal waves. The modal variability is also important, and we've seen that mode 2 and mode 3 are more polarized in the direction of the wind, and as a consequence are more affected by this energy sink. And yes, these results have been published in a paper which was published in Scientific Report last year, called Wind Current Feedback is an Energy Sink for Oceanic Internal Waves. There are more details available in this paper than what I have presented here. Of course, this study has, I mean, this was very preliminary as just to explain a new mechanism, but it still has very strong limitations. First of all, it's a regional study, so the results might be different in a different region because it completely depends on the local configuration of the winds with respect to the currents or the currents associated with the internal waves. And so it would be really interested to look at how this energy sink might be, or how strong it might be in other regions, such as the Hawaiian Ridge, the Luzon Strait, where we know we have a strong generation of internal waves, internal tides mostly. Then these studies, so it relies it's a modeling study, and it relies on the parametrization of the current feedback, which was implemented in a configuration or which was like implemented and empirically developed and validated for mesoscale eddies, but not for internal waves. And it would be really great to see how these conclusions translate in a couple numerical simulations, because that would be the only real way to fully represent those interactions without going through parametrization. So it's a strong limitation of the study, and we hope we can do this in the future. And finally, this numerical model does not resolve the full complexity of the interactions at the air-sea interface. For example, we do not explicitly represent internal waves, surface gravity waves. And it will be interesting to see how these unresolved surface processes can modify the interactions between the internal waves and the winds. And most of these limitations are also perspectives of this work. We're planning on trying to assess the energy sink associated with the current feedback on a global scale in couple numerical simulations. That would be great to use, like, for example, those kind of simulations that are produced at GPL, which covers the entire globe at a very fine scale resolution, which are coupled and also have internal waves represented. And then other process studies with three-way numerical simulation coupled with ocean, atmosphere, and surface gravity wave will also help, of course. And finally, some observations would be also great to validate this kind of processes. Okay, I think I finished the presentation, so I thank you very much for your attention. Sorry again, I couldn't be in person, and if you have any question, you can write me an email. So here is my email address, and I'll do my best to answer them. Thank you. Bye.